Hello and welcome to ML Mania. In this video, we'll explore solving multi-armed bandit problems using action value methods, which is an important concept in reinforcement learning. If you find this video helpful, don't forget to leave a like and consider following the channel for more content like this. Let's get started. This video is based on Chapter 2 of Sutton and Bartow's textbook titled Reinforcement Learning and Introduction. If you prefer reading, check out my Medium article on this topic, and to access the Python code used in this video, please visit my GitHub repository. You can access all these resources by scanning the QR codes on screen or by following the links in the description below. The multi-armed bandit problem allows us to study the balance between exploration and exploitation in reinforcement learning. Imagine a slot machine with multiple levers, each corresponding to an action that yields a reward drawn from an unknown probability distribution. Your goal is to maximize cumulative rewards over a sequence of choices. At each step, you pick an action and receive a reward based on its distribution. The challenge lies in estimating which action offers the highest expected reward while ensuring you don't miss out on potentially better alternatives. Let's formalize the multi-armed bandit problem mathematically. At time step t, the chosen action is denoted by a sub t and the reward by r sub t. The true value of an action A is the expected reward when action A is taken, which is expressed as the equation q star of A equals the expected value of r sub t given that a sub t equals A. This true value is unknown to the agent, so we estimate it based on observed rewards. The estimate q sub t of A ideally converges to the true value as more information is gathered. At each time step, the action with the highest estimated value is the greedy action. However, always choosing greedy actions risks missing out on better rewards. This leads to the exploration-exploitation trade-off. Exploitation focuses on maximizing immediate rewards by selecting the greedy action, while exploration involves trying other actions to gather information and improve long-term outcomes. Balancing these strategies is the essence of reinforcement learning and the multi-armed bandit problem. To maximize the total reward in the multi-armed bandit problem, we need to estimate the value of each action based on observed rewards. One natural method is to take the average of the rewards received for each action and use these estimates to guide future decisions. The simplest way to estimate the value of an action is to compute the sample average of its rewards. At time step t, the estimate for an action A, denoted as q sub t of A, is calculated by the following equation. The estimate of action A equals the sum of rewards received for that action divided by the number of times that action has been selected. Here, we use an indicator function which equals 1 if action A was selected at a given step and 0 otherwise. This ensures we only include rewards for the chosen action in our calculation. If an action has not been chosen yet, the denominator is 0 and we initialize the estimate to a default value such as 0. Over time, as we select actions and gather more rewards, the sample average estimate converges to the true value q star of A, thanks to the law of large numbers. This is why the method is known as the sample average method. It updates the estimate by averaging the observed rewards for each action. The sample average method provides reliable estimates of action values, but it requires storing all past rewards and recomputing the average at each step. This becomes computationally expensive as the number of actions and steps grows. Instead, we can use an incremental update method to compute action values more efficiently. Rather than recalculating the entire average, we update the estimate incrementally. If r sub n is the reward received after the nth action, the updated estimate is calculated by the following equation. The updated estimate equals the old estimate plus 1 over n times the difference between the reward received and the old estimate. In this formula, q sub n is the previous action value estimate, r sub n minus q sub n is the difference or error between the new reward and the current estimate, while 1 over n determines how much the new reward influences the estimate, known as the step size. This method efficiently incorporates new information, with older rewards having less influence over time, making it both computationally and memory efficient. The effectiveness of a reinforcement learning agent in the multi-armed bandit problem depends on how accurately it estimates action values and how it selects actions. This choice, called the action selection strategy, directly impacts the agent's ability to balance exploration and exploitation. A simple way to choose actions is through greedy action selection, where the action with the highest estimated value is always selected. This approach exploits the agent's current knowledge to maximize immediate rewards. However, it is a major drawback. By always choosing the greedy action, the agent fails to explore other actions that could yield better rewards. As a result, greedy action selection is prone to getting stuck in local optima. To overcome the limitations of the purely greedy strategy, we use Epsilon-Greedy Action Selection, which balances exploitation and exploration. At each time step t, the agent selects the greedy action with a probability of 1 minus epsilon, where epsilon is a small value of less than 1, or it selects a random action with probability of epsilon. The advantage of this selection strategy is that as time progresses, every action is eventually sampled enough to ensure the action value estimates converge to the true values Q star of A. The value of epsilon controls the balance between exploration and exploitation, as a high epsilon value leads to more exploration, helping the agent discover better actions, while a low epsilon value results in more exploitation, prioritizing immediate rewards. Choosing the right epsilon value is crucial to achieve a balance between learning and optimizing rewards over time. Now, let's walk through the implementation of the greedy agent. The full code can be found in the GitHub repository linked in the description. Firstly, we initialize the agent with the number of actions in the bandit, an array of zeros to store the estimated value of each action, and an array to track how many times each action has been selected. The update estimates function handles the updates to action value estimates after receiving a reward. This is done using the incremental update formula we discussed previously. Lastly, the select action implements the greedy action selection strategy and simply returns the action with the highest estimated value. Now, let's look at how the Epsilon-Greedy Action Selection strategy is implemented in the select action function. With the probability of epsilon, the agent selects a random action. This ensures the agent occasionally explores actions it might not otherwise have selected. Then, with the probability of 1 minus epsilon, the agent selects the greedy action by choosing the action with the highest estimated value. This simple rule ensures that every action is explored sufficiently over time while still prioritizing actions that appear to yield the highest rewards. To compare the performance of greedy and epsilon-greedy strategies, we ran simulations on 1000 randomly generated bandit problems with 10 arms. True action values were sampled from a normal distribution with mean 0 and variance 1, and rewards were drawn from a unit variance distribution centered on these true action values. We measured the true metrics over 1000 steps and averaged across 1000 runs, average reward, and the percentage of optimal actions selected. This plot shows the average reward for epsilon-greedy agents with epsilon values of 0.01, 0.05, and 0.1 compared to the purely greedy agent. From this plot, it can be seen that the epsilon-greedy agents consistently outperform the greedy agent, which converges quickly to suboptimal actions due to its lack of exploration. Agents with small but positive epsilon values, such as 0.01 or 0.05, strike a good balance between exploration and exploitation, discovering the optimal action more reliably. While an agent with an epsilon value of 0.1 sacrifices early rewards for more exploration, it ultimately achieves the highest cumulative reward. The next plot shows a percentage of time the optimal action was chosen. Epsilon-greedy agents steadily improve their selection of the optimal action over time, while the purely greedy agent performs poorly, often getting stuck in suboptimal actions. Higher epsilon values, like 0.1, lead to faster exploration, but slightly slower convergence to the optimal action, whereas smaller epsilon values improve more gradually but achieve higher long-term performance. From these results, it is clear that epsilon-greedy agents consistently outperform purely greedy agents in the multi-armed bandit problem. While greedy agents exploit current knowledge and often converge on suboptimal actions, epsilon-greedy agents balance exploration and exploitation, enabling them to reliably find the optimal action. However, the best epsilon value depends on the specifics of the problem. For example, in noisier environments with higher variance, it might take more exploration to find the optimal action, meaning agents with higher epsilon values should fare better. If the rewards are deterministic, a greedy method could perform best since the optimal action would be found quickly and reliably. Lastly, in cases where rewards are non-stationary, exploration becomes even more critical. Without continued exploration, the agent may get stuck in exploiting outdated knowledge, missing out on better actions that could yield better rewards. In non-stationary environments, where reward probabilities change over time, using a constant step size can help keep estimates responsive to recent changes. Instead of adjusting the step size dynamically as 1 over n, we fix it to a constant step size alpha, which is set to a value between 0 and 1. This results in the update rule, where the updated estimate equals the old estimate plus alpha times the difference between the reward received and the old estimate. This method gives more weight to recent rewards while reducing the influence of older ones, making it ideal for dynamic environments. All the methods discussed so far depend on the initial estimates of action values, which can bias early decisions. For the sample average method, this bias disappears after all actions are selected at least once. In contrast, methods with a constant step size retain the bias, although it diminishes over time. A simple way to encourage early exploration is by setting optimistic initial values, estimates higher than the expected rewards. For example, initializing the initial estimate to 5 signals to the agent that all actions start with a high reward, prompting it to explore each action multiple times. As rewards are received, the estimates decrease and eventually converge to the true values. This approach ensures the agent doesn't prematurely exploit suboptimal actions during the early stages of learning. We don't show code for this method in the video, because it's essentially the same as the Epsilon-Greedy strategy, with the only difference being the higher initial values. The following plot compares the average reward over time for an optimistic initialization agent with the initial action value estimate set to 5 and an epsilon-greedy agent with epsilon set to 0.1. With a constant step size of alpha set to 0.1, the optimistic initialization method achieves higher average rewards over 1,000 time steps, although it learns the optimal action more slowly due to increased exploration early on. The optimal action selection percentage shows a similar trend. From these results, it can be seen that in stationary environments, optimistic initialization leads to favorable results by encouraging early exploration, resulting in higher rewards and optimal action selection rates over time. While the Epsilon-Greedy strategy encourages exploration by selecting random actions, it doesn't account for which actions are more likely to be optimal. Upper confidence bound action selection improves on this by considering both the estimated value of an action and the uncertainty in that estimate. At time step t, UCB selects an action using the following formula. Actions are selected based on the action A that maximizes the current estimate plus c times the root of the natural logarithm of t divided by the number of times that action was selected. Here, q sub t of a is the current estimate of the action's value, while n sub t of a is the number of times that action has been selected. Ln t is the natural logarithm of the current time step, while c controls the balance between exploration and exploitation. The square root term in this formula quantifies uncertainty. Actions that have been selected less frequently have larger uncertainty terms, making them more likely to be chosen. Over time, as the number of times that action has been selected increases, The uncertainty term decreases for frequently selected actions, shifting focus to exploitation. The constant C controls this balance. A higher C encourages exploration, while a lower C prioritizes exploitation. Selecting the right C value is critical for UCB's performance in different environments. Let's break down the UCB Action Selection code. As always, the full implementation is available in the GitHub repository linked below. The first step ensures that actions that have not yet been selected are prioritized. If there's an action with a count of 0, that action will be selected, guaranteeing that every action is tried at least once before applying the UCB formula. Once all actions have been tried, the agent calculates the UCB values for each action, and the action with the highest value is selected, balancing exploration and exploitation dynamically. To demonstrate UCB's effectiveness, we compared it with an Epsilon-Greedy agent on the multi-armed bandit problem. The following plot shows the average reward for UCB with C set to 2. UCB explores more initially, but quickly converges to the optimal action, achieving higher average rewards over 1000 steps. This is due to UCB's ability to balance exploration and exploitation by considering uncertainty in value estimates. The optimal action selection percentages follow a similar trend. As shown, UCB generally outperforms Epsilon-Greedy agents, except in the early steps when it explores untested actions. While UCB performs well in stationary bandit problems, it has some limitations. Firstly, UCB struggles in non-stationary environments where reward probabilities can change over time as its confidence intervals become outdated, leading to poor exploration. Secondly, in large action spaces, calculating UCB values for every action at each step becomes computationally expensive. This makes UCB best suited for stationary, small-scale problems where accurate action value estimation is key. So far, we focused on estimating the value of each action and selecting the best one. Gradient bandit algorithms take a different approach by learning a preference for each action without relying on explicit value estimates. This method is particularly useful when the goal is to maximize a performance metric directly. In gradient bandit algorithms, a numerical preference h sub t of a is maintained for each action A. These preferences define a probability distribution indicating how likely each action is to be selected. The probability of selecting an action A at time step t is given by the softmax distribution as follows. The probability of selecting an action at time step t is equal to e to the power of that action's preference normalized over all possible actions. Here, pi sub t of a is the probability of selecting an action A, while h sub t of a is the preference for that action, and the denominator ensures all the probabilities sum to 1. Initially, all preferences are equal, typically 0, so every action has the same probability. As learning progresses, preferences are updated based on rewards, shifting the probabilities toward higher reward actions. After selecting an action and receiving a reward, the preference for that action is updated using the following formula. An action's preference is updated by taking the old preference plus alpha times the reward received minus a baseline multiplied by 1 minus that action's probability. In this formula, alpha is the step size and r bar sub t is a baseline representing the average reward up to time t. If the reward exceeds the baseline, the preference for the selected action increases. If it's below the baseline, the preference decreases. For non-selected actions, preferences shift in the opposite direction. This dynamic adjustment ensures the agent focuses on actions that yield better rewards relative to the baseline while maintaining randomness in exploration. Let's break down the gradient bandit agent code. The full implementation is available in the GitHub repository linked below. In the select action function, the agent first computes action probabilities using the softmax formula discussed previously. Next, an action is selected according to those probabilities, ensuring actions with higher preferences are more likely to be chosen. The update estimates function adjusts preferences after an action is taken and a reward is received. First, the average reward, or baseline, is computed using the agent's reward history. Then, the preferences are updated using the formula discussed previously. Here, the one-hot vector ensures only the selected action is directly updated, and actions that were not chosen are adjusted in the opposite direction, reinforcing the existing probability distribution. This adjustment ensures that actions yielding rewards above the baseline increase in preference, while those below the baseline decrease, allowing the agent to progressively favor better actions. The plot below compares the average reward for a gradient bandit agent with and without a baseline on the same multi-armed bandit problem, but with the true values drawn from a normal distribution with a mean of 4 and unit variance. This setup highlights the impact of the baseline parameter. With the baseline, the agent adapts quickly to the shifted rewards, reducing update variance and achieving faster, more stable convergence to optimal actions. Without a baseline, performance significantly degrades due to the lack of this stabilizing factor. Gradient bandit algorithms can compete with other methods but are highly sensitive to the step size alpha. If alpha is too high or the baseline poorly tuned, preferences may oscillate, leading to instability. These algorithms may also converge more slowly than Epsilon-Greedy methods in some cases. However, gradient bandit algorithms excel in problems with large or continuous action spaces or when directly optimizing a performance metric. By focusing on reward maximization rather than action value estimation, they are well suited for complex environments. Comparing the performance of these methods required tuning their respective parameters. To evaluate effectiveness, each method was applied to the multi-armed bandit problem across 1,000 runs of 1,000 time steps, measuring the average reward over time. The key parameters studied were epsilon for Epsilon-Greedy agents, C for UCB agents, the initial estimate for optimistic initialization, which was set up with an alpha value of 0.1, and lastly alpha for gradient bandit algorithms. Each parameter was varied systematically and their performance was plotted. This study shows that UCB performs best in this setup, with optimal results achieved when C is set to around 0.8. When choosing a method, it's important to consider not only peak performance at optimal parameter settings, but also how sensitive the method is to parameter changes. A method that excels under ideal conditions may perform poorly with small adjustments. From the results observed in this study, we can draw the conclusions that in a stationary, low-noise environment, UCB or optimistic initial value agents are best. For non-stationary problems, Epsilon-Greedy agents with a small epsilon value or gradient bandit algorithms with a baseline perform well. In large or continuous action spaces, gradient bandit algorithms are more scalable and would perform better than other alternatives. In this video, we explored key methods for solving the multi-armed bandit problem, from simple strategies like greedy and Epsilon-Greedy agents to advanced techniques like UCB and gradient bandit algorithms. Each method has its strengths, and the best choice depends on the problem and the environment. If you found this video helpful, please leave a like and subscribe, as this helps me out immensely. And don't forget to check out the links below for the Medium article, GitHub repository, and additional resources. If you have any feedback on areas where I can improve, please leave a comment below. Thank you for watching.